So welcome back, everybody. I wanted to just give you a quick overview of this week and with links to what is going to come. So I wanted to wrap up the discussions of the stability of the Hartree-Fock equations. We did almost finish that last week, but there are some small technicalities. And that leads to a condition which we can easily infer from the type of interactions which we have. This is also something which you will encounter in the first midterm. So tomorrow I'm going to make that available. And I thought that we could use something like 10 days. So that means that we start tomorrow discussing it. And then we have a deadline on Monday the 20th. So it's essentially a paper and pencil midterm. There will be some diagonalization parts where you simply need to diagonalize small matrices and get the eigenvalues and interpret those. But that's a pretty small case, actually. So I hope it's going to look okay. But I'm going to make it available on the website early tomorrow morning. I just need to do some proofreading first. Then the next topic is a topic which is, I would say, I really loved it when I saw it the first time when I was a student taking many-body physics. It's a very simple system. It's called the homogeneous electron gas. And it's a system where you can find analytical expressions for the Hartree-Fock equations. And also an analytical expression for the ground state energy of the system. Now, this electron gas has been used as a kind of a simple model for describing, let's say, the conductivity properties of electrons in metals and semiconductors. And the properties which you can extract theoretically are actually in pretty decent agreement with many experimental properties. And for us, doing more many-body physics, this is an interesting case because you can actually benchmark more sophisticated codes with these analytical results. And that's extremely useful. And it's a system, we're coming back to it, it's a system which is very relevant if you're doing condensed matter physics, interest in semiconductor physics, properties of metals, etc. Or if you're doing material science. For us, and this is a kind of long story, because we're going to use roughly 2 lectures to derive the equations. There is I have to say, I mean, you may think this sounds a bit strange, but I love calculating difficult integrals. And the electron gas is a nice exercise in finding different tricks for evaluating integrals with interactions like the Coulomb interaction. And there's a lot of nice mathematics behind calculations of integrals. But besides that, it serves also as an input to a very popular many-body theory, which is called density functional theory. And the energy which we get for the ground state of the system is something which defines a local density approximation in density functional theory. Density functional theory is a kind of kitchen item for people who do material science and also who need a little bit better starting point for single particle basis than what Hartree-Fock theory gives you. So we will discuss density functional theory next week under this kind of common denominator of mean field methods. Then when we're done with the mean field methods, we are going to look at post mean field theories like many-body perturbation theory, copper cluster theory. If somebody's interested, we could also look at the Green's function theory, which would link pretty nicely with what you guys are doing in quantum field theory, because then essentially what we are dealing with is non-relativistic quantum fields. Okay, this was about a kind of overview of what is coming this week and next week, because next week we will discuss density functional theory, but then we need to remind ourselves a little bit about some technicalities. I'm going to use a few minutes on what we didn't finish last time. Okay, so let's switch to the whiteboard. So what we were trying to do last time is actually with a Hartree-Fock Slater determinant, which we labeled with a short acronym. We just call this for C, because we define what is called a core of states up to the Fermi level. Then what we looked at then is a change of this Slater determinant, and we derived Fowler's theorem. So we are looking at a variation of this Slater determinant, which we call delta C. And what we defined last time was a Slater determinant using Fowler's theorem, which then can be seen as a linear combination of particle-hole excitations. So we have a variation here, delta CIA, and then we have a creation and annihilation operator, and these are states above and below the Fermi level, acting on this state C. So this is how we define that one. And what we wanted to show then is that this energy, E Hartree-Fock, is the lowest energy we can achieve with this Slater determinant based on variational calculus. So what we have then is that this expectation value is something which we define like that. And then the quantity which we want, or the thing we wanted to prove, is that this expectation value here divided by C prime, because we are assuming that this C prime is not normalized. So then we need to have the normalization integral, that this one is larger or equal to the one which we get from the Hartree-Fock calculation. Okay, this was roughly what we wanted to show. Now, the thing which we did last week was then to calculate the contributions to the numerator and the denominator. And where we ended, so I'm just going to set up the final expression which we got. So we got a series of terms here. So we can show then that this quantity is something which can be written as, so this C prime of C prime divided by C and C prime is then given by the Hartree-Fock energy, which is the one we wanted to be the lowest one. And then we made an approximation here. So we have to put an approximation sign where we have a term delta E, which I'm going to set up again, divided by the normalization factor. So plus AI, a sum of AI, and then I have a delta CIA squared. So what we did then was to keep terms to second order in delta C. Obviously, we have higher order terms, but we're assuming that they are very small, because delta C is assumed to be a small variation of the wave function. And in all the variational calculations, which you probably have encountered in different courses, you would normally always truncate the expansion at the level of the coefficient delta C squared. So let us quickly remind ourselves about what these terms are in this delta E. So one of the assumptions we have to make in order for this one to be true, what you see here, so this is exactly what we want to prove, then we simply have to require then that this delta E should be larger or equal to 0. Because if that is the case, then that state which we have found is going to be the lowest possible energy we can get for the ground state with a given Slater determinant. Now, so what I want to do now is simply to remind you of what these different terms look like and when we made the approximation. So let me quickly remind you of this calculation which we did last time. So this is something which we can then write as a, so let me just put up the terms here. There is a term E0, Hartree-Fock, which is multiplied with, and now I'm just going to be a little bit lazy here. So I'm just going to plug that one in. And when we divide with this denominator, when we divide that away, that's when we get the expression which you are seeing here. So I'm just reminding you quickly of some of the terms, and then there's a new term which now contains a summation over particle Hall states. And this has, and you will see that all these terms, which involve the interaction and the other terms of the Hamiltonian, they come at second order in these coefficients delta C. And then we had a sum over epsilon, the Hartree-Fock energy for the single particle states, like that. And then there is a new term plus a Bij, and then I have a delta CIA complex conjugate, delta CJB, and then I have an integral AJ of VIB, anti-symmetrized. And then we have two new terms, which we also went through the calculation of. So this term, which you see here, is what you would get. So let's just re-emphasize it. So these two terms, let's put dots around them. These are so-called one particle, one hole contributions. So this is the matrix elements which you would get when you look at the one particle, one hole block in the FCI discussion, which we had last week and the week before. So this is essentially, this part here is us taking the transition from one particle, one hole state to a new one particle, one hole state. Then we got two more terms. So we got a term plus 1/2, and this is given by a AIBJ. And then I had a terms delta CA, delta CJB, and then I had a matrix element or integral of AB anti-symmetrized. And finally, there is a new term, which now also runs over AI and BJ, but then I have a delta CIA, and then I have a delta CJB complex conjugate, both of them. And then I simply have the emission conjugate of the integral which we had in the previous term. So these two terms, obviously they're higher order terms, but we stop at the delta C squared. Now, these terms which you see here now, they correspond to us having taken the overlap between zero particle, zero hole, the Hamiltonian, and then a two particle, two hole excitation. So we are now mixing in a two particle, two hole excitation. The previous one was actually a overlap between the one particle, one hole state and a one particle, one hole state. So these terms are terms which we can rewrite. And what we are going to do then is to rewrite those terms in using a matrix, a compact matrix notation. So let's now look at these specific terms here. So when you look at the first term, first one, so I'm going to put some numbers on them. So I'm going to call this for 1. This is the first term. And then I have a 2 here and a 3. I'm going to rewrite this so that this object delta E is going to look like a matrix. Because in principle, these summations over A and B, etc., they run to infinity. But we are going to truncate the summation over A and B. So these are going to be finite sums in an explicit application because you cannot sum to infinity, which means that we are going to translate these equations, which you see here, in terms of a more compact matrix equation. And from the matrix, then we can say something about this delta E. So I'm going to rewrite everything you see here, these terms 1, 2, 3, as matrices. So this delta E, which we have, this delta E, is now going to be this term here, and this term here. So let's just look at how we can rewrite it. So let's take the first one, the I term here. So let's switch over to the other side here so that we have more space. So we have a summation ABIJ, and then I have a delta CIA, and a delta CJB, and then I have different terms. I have an epsilon A Hartree-Fock. This has actually a delta AB, delta IJ, and then there is a minus an epsilon I Hartree-Fock, and that also carries with it the same Kronecker deltas. And finally, there is a integral of VIB here, anti-symmetrized. So what I'm going to do now is to define a new variable, which is now a particle hole excitation, so AI. So you can read this as a one particle, one hole excitation. And then I'm going to define a new variable, J. So I'm going to lump together the summations over A, B, and I, and J in terms of one particle, one hole excitations. So what I'm going to define now is that this specific integral, AJ, VIB, anti-symmetrized, is something which I will call for a new object. So this is going to be a matrix element of a matrix A, and then I set this as an A and BJ, and this is going to be an A of I and J. So normally a matrix element, when I label it, I used to use lowercase letters, but in this particular case, I'm going to use an uppercase letters. I hope that doesn't lead to any misunderstanding. Now, if you look at this term, and you want to if we want to add this as a Feynman diagram, you could actually rewrite this one. If you just open up one of them, so you would have a state A coming out, and you have a state I coming in, and a state B coming in, and a state J here going out. So this is a typical one particle, one hole excitation diagram. So how can we see that? So the way you can think of it is that you, at an initial time, you destroy a particle hole pair here, and then you create a new particle hole pair. So you had a particle hole pair, and then you get a new particle hole pair. This is a way to interpret that specific contribution. So this is how we're going to rewrite that term. And that means also, if we now look at the notation we have introduced, I'm going to write this term CIA just as a delta CI. And then obviously the last term is going to be a delta CJ. So let's bring in further definitions here. So we have all the terms which are needed. So then you can see that we have a delta CJB is simply going to be a delta CJ, like that. And then I'm going to define a new term, which I call delta epsilon IJ, which is simply going to be epsilon A Hartree-Fock minus epsilon I Hartree-Fock multiplied with delta AB and delta IJ here. So you see then that parts of this matrix delta E can now be rewritten in terms of these elements, A, and this delta epsilon, and the delta C's. Let's do some further definitions. So if I look at the second term, and in the third term, I'm going to have this integral, Vij, and if we have it anti-symmetrized, so let me just quickly remind you of what that looks like. Ij minus, and then I would have Ba of Vij. Now, if you want to interpret this in terms of a diagram, we would get something which looks like this. So we have the A and B's going out, and I and J's coming in. So these are an incoming hole states. And so we have R, B, and then J. And this is A. When we put labels on everything, this is something which we would call a two-particle two-hole excitation. So we had two-hole states, which then get promoted to two-particle states. So when you see a diagram like that one, you can interpret that as a two-particle two-hole states being created. So you start with two-hole states, you remove these states below the Fermi level, and then you promote the two particles up in an excited state, A and B. And you've created a two-particle hole pair. Now, this term here is a term which we, with the same kind of notation, we are going to relabel that one in terms of B, a matrix B, with components B, I, J. So I and J are still one particle, one hole states. And then we have the final one, which is going to look like as follows. And then I have the IJ, V, AB, anti-symmetrized, and I'm going to put that one equal to complex conjugate of I and J. So then what I can do is actually to write this term which we looked at. So this delta E term, if we now do this delta E is something which I can write out as a sum over I and J instead of a sum over particle hole states A, B, and I, J. And then what I'm going to get is a delta C, I, complex conjugate, and then there is a delta C, J. And this is multiplied for the first term, we have a delta epsilon I, J. And this obviously also contains a Kronecker delta with delta IJ here, plus this AIJ, like that. So just as a reminder, if you're thinking of a matrix, if you have a vector A matrix A, and a vector X, then this is the nothing but IJ, and then you have XI, AIJ, the matrix elements, and then XJ. Just as a quick reminder. So what I did now by changing this I and J's and A's and B's in terms of the uppercase letters I and J, I have just introduced another way to perform the summations. And this is normally what is done. Instead of you summing over a quadruple loop, you actually can reduce this to a double loop. And this is often much more efficient from a computational point of view as well. Then what I'm going to define now is a further component. So I'm going to define this delta E with this kind of trick which we have here. So we will also have plus a sum over I and J, and then I'm going to have a delta Ci, a delta Cj, and this is going to be given by, if you now look at the notation which we had here in the previous case. So here we have a delta Ci Cjb, and then for the other component which we have here, we have this complex conjugate components. So we would now get delta Cib, and then we have the matrix, which is this one, the one here. This is going to give us, so let me just be correct now, that should be, yeah. I have B, Ij, plus the final one, which is an Ij and delta Ci, and delta Cj times Bij here. And this is something which I now can rewrite as a matrix. And I'm going to rewrite my delta E as a matrix, which is going to look like, we have a vector X, which we are going to define. I have a matrix M, and I have a vector X here. And X is simply going to be, so let me just put that one up here. That is going to be a delta C vector and a delta C complex conjugate, like that. The matrix M then is going to look like as follows. So the matrix M, and you will see that when I now perform the vector matrix multiplication and then the multiplication with a new vector, you're going to get back the equations which I showed you earlier. So the matrix is going to be given by a delta epsilon plus this matrix A. I have this matrix B, I have this one here, and then I have delta E epsilon plus A here. Now A here is essentially going to be the same as A complex conjugate. And then you see that in order for delta E to be larger or equal to 0, then M has to be what we call semi-positive definite, which means that the eigenvalues of the matrix are larger or equal than 0. Which means that eigenvalues, all the eigenvalues, lambda I for this matrix, have to be larger or equal than 0. Then, when you are looking at a matrix like this one, and you want to figure out whether this is a positive definite or semi-positive definite, you don't want to calculate the eigenvalues, because the eigenvalues, to calculate the eigenvalues, if the matrix is large, this is something which requires quite many floating point operations. But there is a necessary but not sufficient condition which deals with the diagonal matrix elements. So a necessary but not sufficient so by inspecting the diagonal matrix elements, you can already say something about whether this matrix will be semi-positive definite or not. Is that if I take one of the diagonal matrix elements, actually we are summing up all the diagonal elements. So these elements, which run like this, of V of IA, so these are the diagonal ones, AS, have to be larger or equal than 0. So what you can do after this long excursion, the important point is the matrix which you have here, where we have simply rewritten the stability of the Hartree-Fock condition in terms of the higher order terms, delta E. So we can, if we can diagonalize that matrix, we can quickly see whether these are larger or less than 0 or equal to 0. And then if we don't want to diagonalize, but want to quickly inspect the matrix and see if it's possible that the Hartree-Fock conditions are obeyed, then we can simply look at the diagonal matrix elements and inspect them. It's not a guarantee, but it's a necessary condition. I don't know how much you've seen of this in linear algebra courses, but you will often encounter iterative schemes where you actually start with a guess, and the matrix is the same through all the iteration, but what changes are the eigenvectors. And then in many iterative schemes, you have a condition that if in order to converge to the solution you want to, then the matrix has to be either positive definite or semi-positive definite. So if you met iterative schemes like Gauss-Seidel or Jacobi's method, they are methods where you can actually inspect from the property of the matrix and see whether this method will converge or not. I don't know if you remember or you met methods like Jacobi's iterative scheme, which is extremely powerful. That is a method which converges to the exact solution if the matrix is positive definite. So this is, I would say, a very nice way to inspect the problem in case you're in doubt whether your Hartree-Fock solution converges or not. So in the first midterm, we're actually going to encounter, at the end of the midterm, we are going to calculate this stability condition for the Hartree-Fock method. And then considerations like this one become important. So the first midterm is essentially about Wick's theorem, some FCI, and Hartree-Fock theory, obviously, because these are the topics which we have covered. I was tempted to do the electron gas, but that means that you would not have seen that before today. And one should have for the midterm things which you have seen. When I was a TA, I actually had a colleague who loved to make exams with things which people had never seen during the lectures. Okay, so what I want to do now is to go a little bit back to the slides, and we are going to look now at the electron gas, because that's the topic which will keep us busy this week and next week. And we are going to use, as I said, the results of the calculation of the ground state energy as an input to a very popular approximation which is made in density functional theory. And this is called the local density approximation. And that uses the results from the energy of the ground state for the homogeneous electron gas. But I wanted to give you some words first, and then we are going to look at the mathematics which describes the electron gas, so that you get some feeling of what the system is. So this is a homogeneous system, which means that, and it's an infinite system, which means that we can also actually use plane waves as an ansatz for the wave function. And due to the translational invariance of the problem and the interaction, the plane waves are also going to be the Hartree-Fock solution. So this is a system due to the fact it's an homogeneous infinite system and the properties of the interactions. The Hartree-Fock method is going to give the same eigen functions as we would get when we look at the non-interacting case, which is just kinetic energy. So that means I need to remind you guys a little bit about the particle in the box calculations, because that's the starting approximation. I hope you don't get offended if you see the particle box in a box again. Okay, this is the, because these are going to be the eigenstates of the kinetic energy. Then the only thing which changes in this type of calculations is the energy. So when we do Hartree-Fock for an infinite system, a plane wave is going to be the eigenfunction of the system, or the Hartree-Fock equations. But what changes is obviously the energies. And this is what we are going to derive through manipulations of different integrals. And that's essentially what the first part is about, to derive the Hartree-Fock energies. And that's what we will do today. And tomorrow, we will start looking at the calculation of the total energy. Okay? So I wanted to go through some of this by slides, but then with the calculation, the explicit calculations, we are going to go back to the whiteboard. So let me just bring this up. Let me just do that one. Oh. So let's do that and then bring up the full screen here. So the electron gas. I'm just going to repeat some of the things which you see here. So it's one of the few realistic models. It actually gives a decent approximation to experiment, where you have a system of many particles that allows for analytical solutions of the Hartree-Fock equation. It also allows for a nice analytical expression for the ground state energies. So it's actually one of the few cases where we can do that. And it gives a very good approximation to properties of valence electrons in metals. And there are some basic assumptions. So this is a system of electrons that is not trapped by some external forces. So if you think of an electron in an atomic, in an atom, like atomic neon, then you know that there is a atomic nucleus which sets up an effective force which attracts the electron, and that binds the electron. So the motion of the electrons is constrained within a certain distance by the attractive potential which is set up by the atomic nucleus. So if you have 10 protons, that will obviously set up an attractive interaction between electrons and protons. So what we are assuming then is that the only thing which the electrons have before we set up an interaction is kinetic energy. And the kinetic energy for an infinite system is essentially given by plane waves, also by a free particle. And the attraction then is provided by a uniform background of ions. So instead of you having ions which are scattered in specific or placed in specific positions like you would have in a lattice, in a typical material, a periodic lattice, then the background is assumed to be just a homogeneous background, which is smeared out. So the electrons move with kinetic energy, and they see a uniform background of ions. So ideally, when you look at a system like this, if you wanted to, so let's just go back quickly to the whiteboard. So just to let you make some kind of or develop some intuition, if you think of a typical material where you have some kind of periodic lattices, so what you will have then, if this is a cubic lattice, imagine this is a cubic lattice. I told you that my drawing skills are just horrible, but you could think now that in each side here, there is an ion, one atom, and then these electrons would be moving in between. So you could think of an electron here, an E-, which moves in this background. This is the standard approximation which you would encounter if you take a course in condensed matter physics and you look at, let's say, a material with a periodic set of lattices. So because many of the, in a solid, you can actually approximate the way the atoms or ions are organized in terms of these lattices which just get repeated. And then you have electrons, these so-called conducting electrons, which just would move between the potential set up by these ions. Now we are going to smear out the charge of these ions. So you could think that each one of these ions sets up a positive charge, which then the electron sees, and that obviously changes the motion of a particle. But we are going to look at this system as a system of a uniform background charge. Okay, that was one of the approximations which we're going to make. If you're dealing with a solid state problem, you would then often encounter some type of lattices which reflect the symmetry of the system. So let's just go back to the slides. The other thing is that we assume that these ions are stationary, so there's a stationary background. The system as a whole is neutral. And then what we are going to do now is to place a given number of electrons. So when you actually run calculations of such systems, you cannot run a calculation of the infinite electron gas, but you have to approximate it with a given number of electrons. And then you would increase the size of the number of electrons and let that go to infinity, and you would let the volume go to infinity. Now, what is a constant is the ratio between electrons and the volume, which then defines the density. So we are going to assume that we have a cubic box of a given length, and that will also give us some specific quantum numbers. So we are coming back to that. And then we have a volume which contains a uniform distribution of positive charge. So that means that we would have a charge density. So the density is the number of electrons divided by the volume. And when you multiply that with the charge, then you have what we call a charge density. Okay? So these are just definitions. Have you encountered a system like this if you took a course in statistical mechanics? You probably did. Okay, I'm going to gradually bring in this thing. So it's a system of electrons that is not influenced by an external force, and they give rise to a uniform background, just to summarize. And the ions are stationary, and the system as a whole is neutral. So irrespective of simplicity, this system in both 2 and 3 dimensions has actually eluded a proper description of correlations. except if you run Monte Carlo calculations. And the first set of these calculations were done by David Zeppeli and collaborators in the 80s and 90s for the 2- and 3-dimensional electron gas. So it's an interesting testbed for studying electron-electron correlations. And it's in particular important as a cornerstone of the local density approximation in density functional theory. So what we are going to do now, and you might think, I mean, why are we going to spend 4 lectures actually on deriving this contribution to the energy? But it's useful to have seen it because density functional theory is a very popular many-body method, a mean field method. And often this quantity is just assumed that people know where it comes from. But there are actually some calculations behind it, which I want to go through here. And there's a lot of similarities to real systems, and you can find this in alkali metals and doped semiconductors. The 2-dimensional electron fluids are seen on metals and liquid helium surfaces, as well as metal oxide semiconductor interfaces. So it's even though here it's an academic problem, an academic system, it has lots of connections with real life applications. There's another thing which also makes this system very interesting. So there is what is called a phase transition in low dimensional systems, which is called a transition to a Wigner-Seitz crystal. So what happens when these electrons, if you suppose you trap these electrons in a harmonic oscillator trap. Now, when you make the trap wider and wider, that means that the oscillator frequency becomes smaller. When the trap is wider and wider, on average, the 2 electrons are actually more apart from each other. But there's something which happens then, which is counterintuitive. So one thing, if you think of the harmonic oscillator, when you make it wide, a small oscillator frequency, the kinetic energy goes to 0, which means that the electrons become more and more localized. Then when they become more and more localized, you have a transition from what's normally called a Fermi liquid to a Wigner-Seitz crystallization. So these are things which actually observed experimentally. So the electrons acquire 0 kinetic energy. But what becomes very interesting then is that if you have a Coulomb force which is not damped in any way, then the long-range character of the Coulomb force kicks in. So you have a dilute system. The electrons are far apart from each other. And then you would expect that the Coulomb force should be less important. But what happens then is that correlations become more and more important. So this is a case which is very interesting from a theoretical point of view. And you will see that methods like many-body perturbation theory we will discuss, and also copper cluster theory, which are methods which expect that the spacing between the Fermi level, states below and above, is pretty large. These methods break down because you are getting in a strong admixture of many one-particle, one-hole states. And this is due to the long-range part of the Coulomb force. So you would think this is a dilute system, the interaction should be weak, but the Coulomb force has an infinite range if it's not screened. And then what you will see is that these correlations become more and more important, and certain many-body methods, they just kneel down and they are useless. So it's a very interesting problem because there are many, real-life systems which actually are close to a Wigner-Seitz crystallization. Okay, that was a kind of detour here. So after the break, we are going to remind ourselves about some properties about plane waves. And when we are going to look at the homogeneous system in the limit where volume goes to infinity, then the solution to the problem is going to be given by a plane wave multiplied with the spinors we have for spin. So because we are dealing with a spin up and spin down system. But I'm going to remind you of some of these technicalities after the break. So when you run the calculations, you typically run this with a finite volume and a finite number of particles. And then you take the limit, volume and number of particles goes to infinity. That's normally what we call the thermodynamical limit. And the ratio between the number of particles and the volume should be a constant, and that defines the density. So the two quantities by themselves go to infinity, but the ratio stays constant because the density is something we want to keep as a constant. Okay? So after the break, we are going to look more at the gritty-nitty details here, which we need in order to perform the Hartree-Fock calculations. Oops. So welcome back. And now the focus, this lecture and also tomorrow, is essentially going to be a derivation of the Hartree-Fock energies, and also for the single particle states, and also the ground state energy. And that will lead to what I mentioned, to what is a common approximation in density functional theory, which is called a local density approximation. So before the break, we said that we are going to look at the system in a box, and we are going to run calculations with a finite volume and a finite number of particles, and then we're going to take the thermodynamical limit, which means that we let the number of particles and the volume go to infinity, but the ratio between them stays constant. So the density, which is the number of particles divided by volume, is a variable which stays constant. And the total state of the system for a single particle state is now given by the wave number, which is just h bar multiplied with k, giving us the momentum. I guess this is something you are pretty familiar with. And this is the wave function here. The plane wave function is then multiplied by the spinor here. And this is something which we discussed before the break. Now, I wanted to quickly remind you of some of the properties which you probably have seen in basic courses in quantum mechanics. So when you dealt with a particle in a box with infinite walls, then what you found, since a particle in a box with infinite walls means that between the walls, it has only kinetic energy. Then the kinetic energy is this quantity Ki squared multiplied with the h bar squared divided by 2 times m, the mass of the particle. And this object here is something which is quantized. We know that from other types of such equations with 2-point boundary values. So if you're looking at a string, which is fastened in both ends, the energy of that one and the momentum is also quantized. But you would never be able to measure the difference if you take a real string and you put that into vibration and you take its mass and its weight and the length of it as the physical parameters, and you try to look at the energy difference between two possible states, you would never be able to measure that because that energy difference would be on the order of something like 10 to the minus 20 or even less electron volts. However, when you come to atomic, molecular, nuclear physics systems, systems in condensed matter physics, quantum chemistry, you can actually find energy differences which are within the reach of the experimental setup. So the energy, if we look at the motion in 3 dimensions, the energy and the momentum is going to be quantized. And we are going to set up a Hamiltonian now, which will contain obviously kinetic energy, and it's going to contain potential energy. So the Hamiltonian is going to contain, if we now look at the electron part only, so this is the electron part, that is going to contain a Coulomb interaction, which we are going to screen. So this is a calculational trick, which you will see why we are doing that, because unless we screen it, we will have some divergences in the calculations. But then we are going to use this as a technical aspect, and then we take the limit where mu goes to 0 and calculate the final Hartree-Fock energies. So if you let mu be 0, this would be the total unscreened interaction between two electrons, and this would be its kinetic energy. Then there is a background, and then there is also an interaction between the electrons in the background. And we are going to discuss these terms a little bit later. But now I wanted to remind you of some of the basic aspects of this particle in the box problem. So let's just switch to the whiteboard and just remind ourselves about some of these technicalities. Is this something which rings a bell? I mean, particle in the box? This is essentially what you did in quantum physics. And for those of you from UIO, it will be physics 2140. Okay, so let's do physics 2140. So let's just change page. I'm going to call this the electron gas in 3 dimensions. So if we now think back, our first step now is actually to calculate the Hartree-Fock energy for these electron gas. So we have the Hartree-Fock energy, and we can look at states above or below the Fermi level. So we are going to now, sorry, I should have had a P here to indicate that these can be states below or above the Fermi level. So the Hartree-Fock energy here is going to be given by this integral and H0. And H0 is just going to be kinetic energy of P. And then we have the Hartree-Fock potential. So that means that we have a sum over all the states below the Fermi level. So these are the expressions which we have looked at till now. And so we have an integral Pj of V of Pj here, anti-symmetrized. So this is the first thing which we're going to do now. We're going to find an analytical expression for the Hartree-Fock energy in the electron gas, for the electron gas. The other thing which we are going to do then, when we have the Hartree-Fock energies, is actually to calculate the expectation value of the Hamiltonian with the Hartree-Fock Slater determinant, which is going to be given by E0 Hartree-Fock. And this is something which we will begin with tomorrow. So in our case, H0 is just kinetic energy. And it's common to write the kinetic energy as a T, or somebody writes it with a T. We have been a K, we have been using a T here. So this is kinetic energy only. And we know that this operator is given by minus h bar squared. And then we have the second derivative like that, okay? So if we now think of a particle in a box with periodic boundary conditions, I'm just going to repeat some of these basic elements which you may have encountered. You probably saw this in 1 dimension when you took physics 214. So for a particle in a box with infinite walls, in a box, and we are going to think of this as a 3-dimensional box with infinite walls, then there's only kinetic energy which plays a role. So that means that the potential energy is infinite at the walls. So then we have a wave number which is quantized. And this wave number is then given by 2 pi divided by L. And then I have an N1 times an E1. So these are the unit vectors. It could be in the unit vector in the X direction, the Y direction, and the Z direction. Now I'm just labeling them as an E1, E2, and E3. And we know that these numbers, N of I, they are given by 0, plus minus 1, plus minus 2, etc., to infinity. The solution then, which we would write as in terms of the wave number, is given by 1 over omega, which is the volume, multiplied with E. And now I'm dropping spin here. Just note that for simplicity. The reason for that is that our Hamiltonian is going to be spin independent. So the kinetic energy doesn't change the spin. So we are going to drop the spin degrees of freedom when we don't need to care about them. When we are going to look at the direct and exchange term in the expectation values of the energies, then we need to look at the explicit spin degrees of freedom. The interaction, the Coulomb interaction, is spin independent, but the setup of an expectation value depends on the spins of the particles. And in the exchange part, if we have spin up and spin down as our state, then the exchange part is something we have to look more carefully at. But we are coming back to that a little bit later. Now, what that means, when we now look at the kinetic energy, if I act with the kinetic energy on this specific state, what this is going to give me, because I just take the derivative twice, so that gives me simply k squared. So I get h times k squared divided by 2m, and this is multiplied by phi k of r, okay? So I hope I can just list these quantities, because I assume that these are things you may have seen before. And obviously the momentum which we have, p squared, is then h squared times the wave number squared. And that means that I can actually rewrite the expectation values of the kinetic energy in terms of just this quantity p squared. So let's just remind ourselves of that. So that means that if I now calculate the expectation value of the kinetic energy operator, and so let's just wait a little bit before I change page here. So if we just set this up, what I would get then, if I now put it like this, P of T of P, and I'm not putting vector signs on the P's here. I could have put that one because I want to indicate that this is not a one-dimensional case, but let's just leave that out. So this is in principle given by the, I'm just setting in the wave function. So I have an 1 over square root of omega squared. I'm integrating over the volume where the particles can move. I have a three-dimensional object here, d of r. And then obviously I'm going to get, when I'm acting with p, I'm going to get p squared divided by 2m. And then I'm going to get the wave function squared, like this. Okay. So this quantity which you see here is just E of I of P times R. So I multiply with H bar, multiply with E of minus I of P of R, like that, right? So that's on the Brownian-Ket side. So what I have inserted is just a D over R, and then I have an E of I P of R divided by the volume, multiplied with the operator T, and then I have an E of minus I of P of R divided by the volume. This is essentially what I've done. So that means that since P is not included as an integration variable, then I simply have P over 2m, and then I have 1 over omega. Let me just write this omega a little bit better. So this is also an m here. And then I have an integral over the volume. That's it. So let's just, and this integral here is nothing but the volume. Since omega of d over r is equal to omega. And I have assumed a finite volume now. So this means that this p squared is actually proportional to, if you now go back to the quantized numbers which we had here, if I now square k, it means that p squared is going to be proportional with n1 squared, n2 squared, and n3 squared, because E1 times E2 is 0, because they are orthogonal to each other. I am assuming that this is an orthogonal basis. So this could be the x, the unit vector in the x direction, and the y direction, and the z direction. So all the cross terms disappear. So that means for us now that this p squared is proportional with n1 squared plus n2 squared plus n3 squared. And then I can set up a table because they will give rise to what we are going to call so-called magic numbers. To magic numbers. And you will see what the magic numbers are when we are dealing with the system in 3 dimensions. So let's make a table, and you will see that quickly now. So let's make a table here where we have n1 squared plus n2 squared plus n3 squared. So this is going to be the value. And then I'm going to break this down in terms of n1, n2, n3. And then I'm going to set up the total number of electrons which I can accommodate with both spin up and spin down. So obviously, since n, the n's can be 0, if you look back here. So these are the quantum numbers which we have. So n can be 0, 1, 2, etc. So when I now look at the energy, and if this is only kinetic energy, so this is a particle in a box with a finite volume box, then we know that we have a 0 here. Then clearly this has to be 0, 0, and 0. Now I can have one particle with spin up and one with spin down. So that gives me 2 particles. Then my next energy changes by 1 unit because I can have n1 equal to 1, n2 equal to 0, and 0. But I can also have -1, 0, and 0. Then I can have 0, 1, 0, 0, -1, 0, and then I can have 0, 0, 1, 0, 0, -1. That makes sense? And for each of them, so I have 6 cases here, and for each of them, I can actually place 2 electrons. So in total, I have 12. This means that my next magic number is going to be 14, which is 12 plus 2. So you could now think of n equal 1 being your Fermi level. So that means that if that is the energy for the Fermi level, the last filled state, then I can actually have 14 particles below the Fermi level. Now, what you will see is that when you take the thermodynamical limit, this number of particles is going to go to infinity. But you can see this kind of magic structure which is going to develop here. But at the end, you are just interested in the thermodynamical limit, which means an infinity of particles. So you can continue like this. So we can put 2 here. And if I have 2, then an option would be -1, -1, and 0. And here, if you do the combinatorics, there are 11 more. So I'm just going to write it like that. I'm not going to set up all these possibilities because this is not very exciting. It's actually you filling in all the boxes with either 1s or -1s so that at the end you get 2, right? So that means that the next magic number, so since I have 11 more, that means that here I can actually take 24. So my next magic number would then be 38. And then you can continue this game. So if I put 3 here, then I could have -1, -1, -1. And in total, there are 7 more possibilities, 7 more, which means that here you can have 8 times 2, so that means 16 in this case. And then you have a new magic number, which is 38 plus 16, 54. And then you can go on like this. Okay? So this is the way you would actually run calculations with different many-body methods. Because when you use a many-body method like, let's say, variational Monte Carlo methods, or you're doing many-body perturbation theory, etc., what you want to do then is actually to, or what you are limited to do, is actually to look at these different magic numbers. You define a Fermi level, and then you would like to make the calculation run with larger and larger number of particles, and then eventually extrapolate to the limit of infinitely many particles. Okay. So let's now look at the, so we looked at the kinetic energy. Let's take a look at the Hartree-Fock potential. So we are interested now in the Hartree-Fock energy, Hartree-Fock potential U of F, and let's set up the expression for that one. So what we want to calculate is P of U Hartree-Fock of P, and this is equal to a sum over all the states below the Fermi level, and then we have a Pj, and then we have a V, the interaction, Pj, minus, and then we have a J, so this is the exchange term, so this is now given by some P of J, of V, of J of P. So that's the Hartree-Fock potential, which we are going to set up. Now let's take a closer look at what this entails. So let's look at a specific integral here. And if we now take and break down this specific summation here, so let's take this specific term. So if you break this term down, what this actually means is a summation over all the states J less than the Fermi momentum, which I'm going to label as a Kf here. But then there is a summation over the spin degrees of freedom. And these spins can take the value of plus, minus 1/2. So previously, when I looked at this J, I didn't care about spins. But now I have to be a little bit careful. So I would have a P, there is a sigma P, there is a J, and there is a sigma J, and then I have my interaction, and then I have a P, a sigma P, and then a J, and sigma J. So one thing you need to keep in mind now is that this quantity here is independent. It's just a Coulomb interaction. It's independent of spin. So when I'm now making the summations, I have to be a little bit careful. So the thing is now that sigma P is fixed, but sigma J can take the values. Sigma J can be plus 1/2, which means that we have a spin of 1, 0, or minus 1/2, which means that we have a spin of 0, 1. Now, if you now look at what you might get when you look at the summations over the spins, what you need to keep in mind now is that these spin degrees of freedom which you have here, so the spin here sees the spin here, and the spin here sees the spin there. The same spin, because this would be particle in the slot 1, and this in 2. So first particle, second particle. So the second particle refers to the quantum numbers here as well. So what it means then is that if you now look at this summation over sigma J, this is something which then simplifies this sum here, because since the interaction does not depend on spin, this becomes equal to a factor of 2. I'm summing over the spins of the particles below the Fermi level. And then there is a summation now over the states, and now I'm just indicating the momenta here, Kf, so up to Kf. So what you could think of now, keep in mind now, I'm going back a little bit. When I say this, what I've done now is to break down this summation here in a spin part, and a part now where the summation over Jk loops over these n values. So if you go back again, the k values are given by the n values, right? So if I'm now summing up states below the Fermi level, and if I have 14 particles in total, it means that I'm summing over all these sets of quantum numbers which you see here. That makes sense? So that summation J less than equal to KF means that now I'm summing over these combinations of N1, N2, and N3. So that's why I can write it like this. Now my spin degrees of freedom, so keep in mind also that the interaction here does not depend on spin. So that means that the spin degrees of freedom are not being acted upon by V. So that means the following. It means that if this guy here is given by 1, 0, then this guy here is also given by 0, 1. No, sorry, 1, that was wrong. That is given by 1, 0. So what I'm doing then is simply to perform the multiplications of two vectors like that. Now in the next case, I'm summing over -1/2, and then that means that then I would just simply have the inner product of 0, 1. So the interaction doesn't depend on this, so I can perform the spin sums independently, and that means that what I'm going to get now is simply something which I'm going to write without the spin degrees of freedom. So this contains only the spatial degrees of freedom, or PJ. Okay? So it's a little bit compact notation, but I hope you can live with that one, or that's acceptable. Now, if we now look at the exchange term, on the other hand, then we have to be careful. So let's just take a closer look at the exchange term. And this is one of these terms which is irritating, because you will always see in textbooks, we omit the spin degrees of freedom because they can be introduced in a straightforward way. But you will see immediately now that if you look at this term, it breaks down into a sum J less than KF. And then we have a sum over sigma J equal to plus minus 1/2. And then we have P, sigma P here. And then we have J, sigma J. So the interaction doesn't do any changes. And then we have P, sigma P. But now we have, now we have to be a little bit careful because we have an exchange term. So we have J, sigma J, and then we have P, sigma P. So let's see what happens now. So suppose now that the sigma P is given by a spin half. So that means that the spinor which we are looking at, this C of sigma J, is going to be given by 1, 0. So now we have to be a little bit careful. No, sorry, sigma, this is, I'm just doing it wrong here. This is sigma P. Okay. So if we look at the spin degrees of freedom, then what we are going to have is something which looks like this, 1, 0. And I'm putting particle 1 here. Now there will be a contribution from sigma J. So we could now have a sigma J here. So this is sigma J, which is also 1, 0, because we are summing freely here, right? So this is particle 2. Now, when we then perform the multiplication here with the ket side, so we would then have a sigma J here. So sigma J, which is going to be given by 1, 0, which is 1. Now this is particle 1. And then we have the other one, which is particle P. So this is sigma P. And now we have sigma P here. That is the exchange part, which is also 1, 0. So when we now look at the terms, this term here obviously has to match this term, and that's 1. And this term here has to match this term. So this is being multiplied This is multiplied with this one. That's the inner product. This inner product is then done with this inner product. So that's fine. That's one. Okay. If we now, however, look at the next term, which would be the term coming from sigma j equal to minus 1/2. So then what we would get then, if we have sigma p here and then sigma j, so in that case, we would have 1, 0, and then we have 0, 1. So now sigma j is equal to minus 1/2. So this is 1 and this is 2. But then we have the exchange term, which then gives us, so this gives us sigma j equal to minus 1/2. So this is 1. But now we have 0, 1. And then we have for the other one, we have 1, 0, which is sigma p. And now you see that if I try to match this one with that one, we obviously get 0. If you then interchange for sigma p, you make sigma p being equal to minus 1/2, you will also get that one of the terms is going to be 0. So that means that the exchange term, so for the exchange term, what we get then is just one term instead of 2 ones. So what we get then is just minus, and then we have a summation over j, all the states up to the Fermi level, and then we're doing pj, and these are now the variables which refer to the momenta, poj, like this. Okay. So what we're going to do now is to calculate these quantities. And now we are going to look at the integrals, and we are going to change the summations with, after some time, we're going to change the summations over the case with an integral. But let's now look at the expression which we have here. So when we now are setting up these integrals, so let's just start looking at the integral. So what we get now, and if we start with the exchange term, this is now going to be given, if you now think of the waves functions, which we are looking at. So the wave functions are given by 1 over omega, and then I have E of I of K times R. So what I will get then is the following. So I will have a integral, which gives me, when I now translate everything, so I have a j less than kf, and then I have this element pj, v of jp. This is going to be equal to this summation over j less than kf. I'm going to plug in the charge which you have in the Coulomb interaction. So this is the electric charge in the Coulomb interaction. And then it's going to be divided by omega squared, because I have 4 wave functions, 2 on the ket side and 2 on the brass side for the electrons. Then I will have an integral over d of r, and then there's going to be an integral over d of r prime. And this is going to be multiplied with E of I. And now what I'm going to do is to use a little bit kind of sloppy notation here. So I'm going to indicate J. This is the momentum for the state below the Fermi level. So I just write that as an arrow. And then I have minus P here. And this is multiplied with R. And then I have a new term, which is E of I. So one is the brass side, and the other one is the ket side, minus J here, times R prime. And then I have to divide that one with the Coulomb interaction, which is R minus R prime, like that. So that's the integral which I need to evaluate now. Okay? Then there is also a direct term, which we have to look at. So let's now look at the direct term. So we looked at the exchange term. So before we do anything now, let's look at what the what the direct term is going to look like. So the direct term that is going to be given by a factor of 2. I'm going to have a factor over omega, and you will see why we only have an omega here pretty soon. There's going to be a summation over j less than kf, and then I have an integral over d of r prime, and then I have an e squared divided by r minus r prime here. So the reason for doing that is that I can actually rewrite this one. If you look back at the integrals you have here, I can now, by a small trick, I can rewrite the integral, because in the other case, what I will have is j plus p times r, and then there will be a minus e to the I of p plus j. So if I do that, I can isolate an r prime and then integrate that one away, and that gives me a volume term. I'm coming back a little bit to that one. I just wanted to set up the expressions. So this term is then going to be equal to, and let me just set this up. This is going to be equal to an n times an e squared divided by omega. And I'm going to have an integral over d of r of e divided by r. So let me just set up these terms first, because I'm going to come back to the way we are going to calculate them. This term here is actually going to cancel the term which comes from the background electrons. I'm going to set up this a little bit later and show you more explicitly. I wanted to run through some calculations first. So this term, and I'm coming back to that, cancels a term from the background ions. Okay, let me just ask you one thing first. So how could I convert this term into that one? That's the number of particles, right? So this sum does not affect what we have here. I'm coming back to how we came to that one. I just wanted to give you the expression which we need now in order to look at the cancellation of this term due to the electron background interaction. So why can I convert that one, this summation, into that one? Any good? This just sums over the number of particles. So this, if you isolate this one, this is just a sum. If we isolate it, this is a sum j less than kf times 1. And that simply counts the number of particles which you have, because this is given by the number of states below the Fermi level. So if I go back to that table which we had, this table here, if I have 14 particles, I would be summing this one, that one, that one, and all these 12 states. So 2 plus 12 becomes 14, the number of particles. So this one translates into the number of particles. The background ions is something which I will set up tomorrow so that you see those terms. But what I wanted to start now is actually with the exchange term and see how we can calculate that one. And then I'm coming back to how I got this specific term and how I can use that term to cancel the one which comes from the background ions. But when we are going to calculate the Hartree-Fock energy, so this epsilon p Hartree-Fock is simply going to be equal to h bar times the momentum k, the wave number, times 2m minus the exchange term. And what we are going to use some time on now is to calculate the exchange term, because that's the term which is going to give us the analytical expression for the Hartree-Fock single particle energies. And then we will come back to some of the other terms a little bit later. So what I'm going to do now is simply to set up that integral again, but I'm going to run some simplifications here. So let's take a look at this. So I'm going to let P go over to K. And in the notation here, I'm going to let J go over to a K prime. So the term which I want to calculate is a term which now is going to be given. So this is the exchange term, E squared divided by the volume squared. And then I'm going to have a summation for all the states below the Fermi level, Kf. I'm going to have an integral over d of r. And this is going to be multiplied with E of k minus k prime. And I'm going to put vector signs because this is a three-dimensional vector. And it's multiplied with r. And then finally, it's going to be multiplied with a d of r prime. And then I have my E of I of k minus k prime multiplied with r prime divided by r minus r prime here. So this integral, the last one, is something which we can calculate analytically. And that's what we're going to do now. So how do we evaluate the exchange term? How do we evaluate this term? So keep in mind that we are at the first stage. We want simply to calculate the Hartree-Fock energy. How do we evaluate the exchange term? And there's a trick you can use here. And the trick deals with us using a convergence factor. So that's the first trick, one. So we're going to introduce a convergence factor, and then we're going to take the limit where this mu goes to 0 after we have done the calculations. So this is a useful trick in case your integral is a nasty one and you have some possible divergences. So then you would calculate with a factor which renders the calculation possible. And then you take the limit goes to infinity afterwards. So convergence factor, then you evaluate integral. And then when you're done, you take the lim of the integral when mu goes to infinity, to 0. So that's the first step. Now, the next step now is us going to an infinite number of states. And here there's a formula which you probably have seen. And this is where we will stop today. So we're going to set up the integral which we're going to solve tomorrow. So the next step is to now let this 1 over omega, the volume of k, and you probably have seen this before, but this maps into of 2 pi cubed, and then there's an integral over k. This is a three-dimensional integral. Have you seen this change from the summation, a finite number of states, to an infinite set of states? Well, some of you have seen it and some of you have not seen it. But this is a common approach which you will find in, if you're not familiar with it, I can give you the right references. So that means that the quantity we need to evaluate, and this is where we're going to stop now, is a quantity which looks like this, 2p cubed. And then I have an integral over d of r. I have another integral over d of r prime. I have my Coulomb guy here, r minus r prime. And then I have an integral over dk prime, because I have a k prime. And then this is now multiplied with e of I of k prime minus k, multiplied with r minus r prime. And then I have this cheating factor where I'm going to let mu go to 0 when, like that. So that's the integral I'm going to evaluate. And this is what we are going to have fun with tomorrow. So if you love integrals, the first lecture tomorrow is going to be devoted to find this one. So I can see the excitement in your eyes, and yet really looking forward to this. But sometimes it's actually useful to have seen these calculations, because this is one of the cases where you can run calculations analytically. Actually, if you just run this through one of the standard tools you have nowadays, it will give you the same answer. But having seen it is actually, I think it's useful. Okay, let's stop there.